thank you. I'd like to thank the organizers for inviting me, and I think I feel confident in speaking for everyone in the room that we should thank the organizers for this wonderful workshop. So today I'd like to talk about non-crossing partitions of a marked surface, and there might be different intended audiences for this. So really what I want to do is tell you about some models. And they all are related to the model of non-crossing partitions. But if you're somebody who uses the model of type A non-crossing partitions like we've been talking about, you might think about whether these models have anything to do with free probability, or maybe you do some combinatorics with those. Maybe there's some combinatorics you would like to do with these other models. If you actually think about the interval from 1 to C in a Coxeter group, and more generally than just the symmetric group, well, I'm going to show you some models that work in affine type for that, in classical affine types. And if you think about marked surfaces, maybe in connection with cluster algebras or with representation theory general algebras or something, then you might be interested in non-crossing partitions of a marked surface. Maybe that has something to do with your setting. So I should say that the first parts of this project were joint work with my former PhD student, Laura Brestensky, and also the representation theory connections, which I may or may not have time to say very much about, are joint with Eric Hanson. So let me move on. So I have to thank previous speakers for basically giving all the definitions that I would need to give. So where we're taking a Coxeter element, we're taking the interval from 1 to that Coxeter element in the prefix order, the absolute order, and this is a lattice. Oh, and look, I think I had a step where I thought my slides have too many words on them, so I'm going to delete words. I think I deleted the word finite right there. So W finite implies that this is a lattice. Now, in class, somehow everything on this slide is something you've seen, except maybe not this. In classical finite types, actually, Caterina's talked about the classical finite types and these planar models, but there's a heuristic that sort of, there's no theorem that I can prove, but there's a heuristic that says if you want to find these planar models, what you do is you take a small orbit of the group and you project it to something that you'd call the Coxeter plane, not a hyperplane, but literally a two-dimensional plane. You project it, and then somehow these tell you what your planar model should look like. And part of the story that I'm going to tell is that this works in affine type also. One motivation for considering this poset from the interval from 1 to C in general is Garside structures for Artin groups, and that we heard about in Barbara Baumeister's talk. Okay, so this is a story that you know. One thing that I want to highlight is that if you want to vary the Coxeter element, you can basically vary the cycle. But then you make choices. You look at for each SI. You look at whether SI is before SI minus 1 or not, and that tells you sort of where to put your numbers in the cycle. Okay, so you do 1, and then the elements that I would call down elements because SI minus 1 precedes SI in increasing order, then n plus 1, and then the up elements in decreasing order like this. So we do 1 up to 7, and then 7 back down to 1. Okay, the other thing that I want to say on this slide is that we like to do convex hulls. In this, I mean, it's the fastest way to make the definition. You say you take the convex hulls of the block of the partition, and then you ask whether those convex hulls intersect. But there's nothing special about convex hulls. It's really a topological condition, right? So you could say that what you really want to do is you want to have blocks in a set partition, and then you want to make an embedding of the block. Maybe our block in the set partition is 2, 4, 5, so I need to put a disk in that contains 2, 4, and 5 and doesn't contain any of the other numbered points, and that's just as good as convex hull. Okay, so just to review this quickly again, Caterina's talked about this. If you want to take type B, signed permutations, then a choice of a Coxeter element, you're really just choosing what I would call a signing of the integers from 1 to n minus 1 if we're in Bn. So you're just going to choose for each number between 1 and n minus 1, you can choose either the plus or the minus. So you get a set of n minus 1 elements, and that's what I would call a signing. And that choice, precisely that choice of assigning determines the Coxeter element. And what's that? And well, let me show you what I'm about to do with that choice of assigning, and then you see if you want to still ask a question. So I'm going to take the assigning. I'm going to make a cycle that starts with minus n, then the signing in increasing order, and then n, and then the opposites of the signing in decreasing order. That's my cycle. Now the reason for this is the Bn has n vertices in its Coxeter graph. There are n minus 1 edges that I need to orient in order to make a Coxeter element. And so the n minus 1 choices, you can record them as these n minus 1 choices. Other questions? Okay. If you want, you can mod out by the symmetry. So we had a symmetric I guess I didn't say this. So the model is centrally symmetric non-crossing partitions of this 2n cycle, specifically this 2n cycle that we got using the signing. But if you want, you can mod out by that symmetry and think of yourself as living instead of in a disk, but in a disk with an orbifold point. So somehow we record the fact that modding out by that central symmetry really left us with only a half circle worth of angles around that point, as opposed to an ordinary point in a manifold. And we record that, and then you can read. Actually, I should go back. In both of these cases, we read the permutation clockwise around cycles, like the cycle notation of the permutation. So that's where I got the minus 5, minus 1, 5, 1, minus 5, minus 1. You can still read the cycle. You need to put in what I would call a toggle line. So if I want to read the cycle with the 5 and the minus 1, I should start at the 5. I pass through the toggle line, which now means all numbers are negated. So instead of going to a minus 1, I think about going to a 1. So I get 5, 1. Now I go back to the 5, but I've passed the toggle line once. And so this is really a minus 5 now. I go back through the toggle line to the minus 1, and if I've toggled twice, it really is a minus 1. So you can keep track of these things if you want. Non-crossing partitions of a disk with an orbifold point. One nice thing that happens here is you're not thinking about central symmetry anymore. All you're really doing is, in this case, n equals 5. You're taking 5 points, and you need to embed a disk. You have a partition. You want to embed a disk, and that disk is allowed to go to either side of the once I choose which points are in it, I can put a disk that goes to either side of that orbifold point, or it can contain the orbifold point. Okay? So you have all those possibilities, and that is what decides that's what your combinatorial object is. It's a set partition together with an embedding of each block as a disk. Yeah, yes, absolutely. That's exactly what you're doing. Yes, absolutely. Okay, so type D, Katarina also talked about this. So you can think of the group of type Dn as even sign permutations. I won't give that definition here. But when you project the smallest orbit, take the smallest orbit of this Coxeter group, you project it to the Coxeter plane, you again get points that go into a circle, but you get 2 points that go into the center. Not 1, but 2. Okay, so we need to somehow be making a model that that has these 2 points at the center. I should say, actually, in all these models that I've been sort of giving the names of people who sort of thought of the model, and then the people who connected it to the interval from 1 to c in each case. So in type D, this was Athanasius Reiner, did both of those steps. And you need to have these 2 points in the center. I'm calling them plus or minus 1 here. There's, again, some combinatorial way to encode a Coxeter element. We won't get into that now. But we need centrally symmetric non-crossing partitions of a disk with a double point. Yes? So that's right. That's how you find, the way you find the smallest possible orbit for a Coxeter group is you want to find the largest standard parabolic subgroup. And then you want to take a point that is fixed by that. Okay, so if you have heard about the surfaces model of cluster algebras, then you'll know that the cluster algebras, that model wants us to actually do type D differently. Now, I should say actually the reason why, well, the reason why the cluster algebras model and the this non-crossing partitions model have anything to do with each other already is also just heuristic. It just seems to work out. I don't know why that should be so either. But if you sort of look at that and compare what's been happening, we should be thinking of, instead of here a disk with 10 points on the outside and 2 double points, we should be again passing to an orbifold in some sense and making that double point into 1 double point. So we would get a disk with 5 points on the outside and 1 point on the inside, which they like to call a puncture. So we should get a 1 punctured disk. This does not seem to work well with non-crossing partitions. So maybe the first lesson here is, if we want to do models such as type D, we really do have to stick with double points and symmetry. You can do this, and you can carry it out in finite type D if you'd like to. But you have to sort of just add this extra information, like, oh, I have to remember really literally whether did the 6 go to the +1 or the -1? You lose track of that when you mod out by the symmetry. Okay, so that's just a quick review of what's going on in the finite classical types. Now let's talk about affine Coxeter groups. When W is not finite, happily I did not leave out the word finite this time on this slide, but when W is not finite, then this interval from 1 to C need not be a lattice. It can be sometimes, but it is not always. Okay? So an affine Coxeter group, just like a finite Coxeter group is a group generated by a group generated by reflections, a finite group generated by reflections, all of which have reflecting hyperplane passing through the origin. An affine Coxeter group is a group generated by a discrete group that acts by affine reflections. In other words, reflection through hyperplanes not through the origin on a Euclidean space. Okay, so McCammond and Sulway dealt with this case. Again, they're coming from the geometric group theory point of view, or the Artin group's point of view, and they wanted a lattice. So in the cases where the interval for 1 to C was not a lattice, what they did is they made a larger group. Okay? So you've got this thing that's not a lattice. You want to put in more elements. It turns out that there's not very many more elements that they needed to put in. John and McCammond kind of worked out exactly where the obstructions to the lattice property were. But what they did is they said, okay, I want a bigger group. I want a bigger poset that's going to be a lattice. Let's add more generators. Okay, so the Coxeter group is generated by all the reflections. That's by no means a minimal generating set, but it's generated by all the reflections. What they said is, let's put in a few more elements that are not already in the Coxeter group and take the group generated by, of course, the reflections and these new elements, or in other words, the group generated by the old group and these new elements. When they do that, they not only get a bigger group, but you can play exactly the same game with the interval from 1 to C, right? You say, now I want all the ways of writing C, not as a product just of reflections, but as a product of reflections and maybe some of my new generators, okay? So you get more paths from, more reduced words, if you like, for C, more paths from the bottom to the top of this poset by adding new elements, and they made a lattice. Okay? So the recent research that I would like to tell you about is to find the planar diagrams that make sense for first of all, the interval for 1 to C in these affine Coxeter groups, and also the larger lattice that McCammond and Sulway made. And this was the part especially that was joined with Laura Brestensky. In type A tilde, the affine symmetric group, things are sort of as nice as you could hope. Okay? So first of all, you get a very natural combinatorial structure of non-crossing partitions of an annulus, as I'm about to tell you. And that model models the larger lattice that McCammond and Sulway defined. And you put a very simple restriction. You say, oh, I'm not going to allow these kinds of non-crossing partitions. And then you're modeling the original interval from 1 to C, the smaller non-lattice. So, okay, you might expect that other types are not that nice. In fact, type C is at least that nice, probably nicer, which as I've learned about affine Coxeter groups, I people have told me, and I've come to believe that type C is actually nicer than type A, which is not what you would think. But okay, so let's talk about just the details of this construction. So we want to start with the heuristic. We want to say, okay, small orbits. Of course, all the orbits are countable. Well, no, I guess there are very small orbits, like trivial orbits, but the non-trivial orbits are countable. So, you know, what should we mean by smallest? Well, there's sort of a way to think about that, and it does relate to what Theo was asking. We want to take the Coxeter group. So we have the Coxeter group acting, and actually this is a good question, because I want the Coxeter group acting as a linear group of reflections, right? On the ambient space, yeah. So we're just, and in the classical affine Coxeter groups, you can actually set things up. If you're familiar with or have seen the models for these groups as sort of permutations with sort of a mod n symmetry and various, you know, variations to get the other types outside of type A, you know, you're basically thinking of them as permutations of the integers. And so your orbit, you can make vectors look like EI, for I now being any integer, right? In the symmetric group, we take E1 through En plus 1 or something, and we permute those. Well, now we have these vectors, and they're not linearly independent anymore. There's some relations among them, but we still can think of these, you know, you're really doing that model for the permutation groups, for the Coxeter groups. The orbit is indexed by these vectors EI. And the projection to the Coxeter plane, there's a lot of details about, you know, we had to think, you know, we at least two different ways you could think of what the Coxeter plane should be, and one of them doesn't work. But you know, modulo those details, you project to the Coxeter plane, and what you get is a bunch of points on an infinite strip. Okay? Now, outside of type A, you get a few points that might land in the middle of that strip, but basically it's a big long strip of points, and there is a translational symmetry that's given by mod n. And so once you have that, what we should do is we should mod out by that translational symmetry and work, instead of an infinite strip, we should work on an annulus. Okay, so just as an example of what this looks like, there is again, actually I think I'm going to be telling you, there's a way to go from, to encode Coxeter elements, and well, actually, no, I'm getting ahead. I should forget I started saying that. If you just take this Coxeter element and project, you're going to get these points. And you'll notice that if I, you know, the n is now 7, this is a tilde n minus 1. If I move mod 7, there's a translation that accomplishes that. That's what comes next. That's what I almost started telling you, and then I remembered the whole next slide is about that. So you had the same thought I just had, but both of us should wait. So I have these vectors that are forming an orbit of my group, right? And I project them all to a certain plane called the Coxeter plane, where there's it's sort of maybe the maximally symmetric two-dimensional plane I could have under this Coxeter group. And I do that, and they land there in these two strips. Okay, there's a lot of, yeah. The point, I think the point is on the next slide. Well, the next slide. After that, that's where really the nicest stuff that you'll like will come, I think. So, okay. Let me just tell you, I guess, a few of the details that I had left out. The affine Coxeter group Sn tilde is affine permutations of the integers. Okay, and what that means is, first of all, they have this mod n symmetry. So where does I plus n get mapped to? It gets mapped to wherever I was mapped to plus n. Is that mod n symmetry. And then there is this, so it's like a normalization condition for this permutation. This makes it so that you don't take your integers and just sort of move everything up, right? It also makes it so that this is a correct model for this Coxeter group. But the sum of, you know, where you send I through n adds up to n plus 1 choose 2. Okay. There's also a larger group that you can consider. And sort of the most immediate, simple next thing you'd want to do. You have this group defined by these conditions. You want a larger group. Let's just take away the second condition. Okay, so you just simply consider permutations of the integers with this mod n symmetry. you almost could let your eyes blur on this notation. If you want to be really careful with what I'm about to write down, so since we have this mod n symmetry, if you have finite cycles, if you have a finite cycle, you have an infinite class of finite cycles in your permutation because symmetry mod n. And then infinite cycles, if I want to explain an infinite cycle, I just need to keep going until I hit something in the same class mod n, and then I've told you everything, right? If I just list those elements. So that's how I'll write down those elements, right? When I get to the next thing that's congruent mod n to a, oh, drat. There's the other typo. There's two so far. This should say A1 plus Qn. There's a law. You know, some people have written things like Murphy's law or whatever. I think maybe there's a readings law, which is typos are invisible until you're standing in front of a group. And there's more to the law. The detailed part of the law is that at that point, whether typos are invisible or not goes according to which thing would be more embarrassing for the speaker. So apparently it would have been less embarrassing for me to, I don't know, whatever. Okay, so the reflections are basically transpositions, but there's this mod n condition, okay? So they're really mod n classes of transpositions. And then there's these special elements called loops, which I'll show you on the next slide why they're important. But this would just, all this does is fixes everything else and takes this element I, right? The loop at I takes the element I to I plus 1, and therefore, I plus 1. Takes the element I to I plus n, and therefore I plus n to I plus 2n, et cetera. And of course, it will have an inverse, which does the opposite thing. These generators, these loops are one thing that you can add in to get the entire larger group. So we have the symmetric group that is the Coxeter group. But if you allow these loops also, you let yourself have reflections and loops, you generate this entire larger group. Okay. Periodic permutations, I've heard of called, sometimes the Coxeter group is called the affine symmetric group. Sometimes the bigger thing is called the affine symmetric group. There's, yeah, I like that. I think that's the best name, periodic permutations. Okay, just a quick example. So if we have Sn, the Coxeter diagram is an n cycle. This is an example with n equals no, this is n equals 7. I don't know why I said 6. Yeah, so, okay, typo number 3. Again, would have been less embarrassing to not notice that, maybe, I don't know. The choice of Coxeter element is recorded again by placing the numbers on the annulus. You've got the details there, but I have to choose an ordering to put S1 through S7 in, right? That corresponds to some elements from 1 to n are placed on the outside of the annulus, and some are placed on the inside of the annulus. And it gets back to the question that was here. It's exactly the ones that some of them go to this top row and some go to the bottom row, and there's maybe no good reason to call one top or bottom, except I drew them that way, and there's no real good reason to say that this is the inside of the annulus, and that is, except that I drew it that way. But, so that's an example. Now we want to talk about non-crossing partitions of an annulus. And I put in a reminder to, at this point, to myself, to remember to talk about Josue's talk. And I think these are related objects. My non-crossing partitions of an annulus, first of all, there are infinitely many of them. And they correspond to permutations. These permutations have infinite cycles. And I think that the two main differences are that the things I'm considering will have infinite cycles. And also, if I'm not mistaken about the annular non-crossing partitions or permutation story, that if I were to take the inside of the annulus and the outside of the annulus and just sort of start twisting them, this is called a Dane twist, but if I started twisting them, I don't think that the annular non-crossing partitions model would say that I changed anything. I think they would say this stays the same. For me, this would, if I sort of twisted everything around and brought the points back to where they started, this is a new thing. So those are some differences. Okay, so non-crossing partitions of an annulus. The general story that I want you to think about is that partitions plus some additional topology, right? In even just back to type A non-crossing partitions, we take partitions, every block gets a disk embedded into this cycle, into this, really embedded into this larger disk, right? With numbered points on the outside. It's the same thing, but we're allowed to do different things, okay? So let me say that an embedded block is one of three things. It could be a disk block. A disk block is just a closed disk and it contains at least one numbered point. Okay, so these are the things that look most like non-crossing partitions that we've seen before. But also you can have two kinds of annular blocks. So let me start actually with a non-dangling annular block. You could have an annular block that is somehow, we've got this annulus. I guess there's no picture of an annulus on the board, but you can picture an annulus, and there'll be pictures in a moment. You have an annular block, and it has some numbered points on the outer boundary, some numbered points on the inner boundary, and of course then the annular block sort of goes around the hole in the middle, just like the big annulus, right? You can do that. That's called a non-dangling annular block, and non-dangling means there are points on the outer boundary and the inner boundary. A dangling annular block is the same kind of thing. We just sort of cut one side or the other loose from numbered points, either on the inner or on the outer. So a dangling annular block, maybe you have points on the outer, and you don't have it doesn't touch any of the numbered points on the inner. Okay, so a non-crossing partition then is just a collection of embedded blocks. The embedded blocks are disjoint. Every numbered point is in some embedded block, so it really is encoding a set partition, and plus a lot of information. And then there's at most one annular block. I think I saw someone sort of squint their eyes, and maybe it was because they saw the at most one annular block. The at most one annular block is, it would be very hard to embed two non-dangling annular blocks. They would cross each other. But I'm forbidding, the at most one annular block is forbidding you to have a dangling annular block that's on the inside and a dangling annular block that's on the outside. So let me show examples. These are some examples. Let me actually address the question that I just sort of asked myself. This is an example of a non-crossing partition with a non-dangling annular block. It touches 7 and 3 and 4. On the outside, it touches 1 and 3 on the inside. So the restriction on not having two annular blocks is what forbids me from sort of just slicing this into two pieces. I'm not accurate enough with my laser pointer to do it, but you just take your laser and you slice it into two pieces. That's not allowed. If I have two dangling annular blocks, one on the inside, one on the outside, I was supposed to have an annular block, one annular block. What's that? E2. Oh, so this is good. No, this is fine. Yeah. What I couldn't do is cut this into two annular blocks, one on the inside and one on the outside. Right. So if you just imagine, sort of, the red. If I take the red part and just cut it into two halves that are both annuli, right? One on the inside and one on the outside. I shouldn't have done that. I should have written what's actually there. Oh, that's actually a clever way to say it. I don't know if you heard what Drew said. You could say that the white space in between must touch either the outside or the inside, and that would be the same condition. That's very nice, and it's also going to connect with Krevera complements, which we'll talk about in a second. Okay, so these are examples, right? We've got no annular blocks in here, but you see that it matters to me how my disks wrap around. Here I've got a dangling annular block in P3, right? Because it touches 7 and 4 on the outside, but touches nothing on the inside, etc. There's a natural way to partially order these things. Basically, if every block of P is contained in in some block of Q, then you put an order relation. Of course, that's up to choosing an embedding that works for that. Yeah. That's right. So there's two natural ways. Actually, maybe there's more. I think there's only two natural ways that you could cut this into disks. One would, you could have a disk. You just ignore the right part and just have a disk there, or you could ignore the left part. And both of those are different from what I have. Yeah. And they're different from each other. Yes, because actually that brings up something that I think I put on the slide but didn't say. We're going to consider these up to isotopy that fixes the boundary. It fixes the boundary pointwise, and so you really can't. That's why we don't get Dane twists and things like this. I need to be able to deform one block into another, the whole partition into another, without moving through the boundary or anything like that, or twisting the boundary. Okay, so the theorem is that this is a graded lattice. The rank function is given by n minus the number of non-annular blocks. I'll let you think about that one. And the proof idea, you can think about the partial order, if you like, as sort of containment curve sets. Curve sets would be curves that stay inside the blocks and connect points, but maybe I'll move on to there. If I want the lattice property, I must have dangling annular blocks. So let's just think about this really simple picture. I've got two points on the inside, 2 points on the outside. Here's my P and Q. If I want the join of P and Q, I need a non-crossing partition that has a block containing this disk and a block containing that disk, and therefore it has to contain some little annulus, that contains 4 and 3, because we're going both sides around the inner circle. If I do not allow a dangling annular block, that annulus would have to connect to something. It would either have to connect to the 1 or the 2, and these would be incomparable minimal upper bounds. If I allow the dangling annular block, I get the join. Okay, so let me tell you about isomorphisms between this whole set of non-crossing partitions of an annulus and the interval from 1 to c in 2 different senses. So we can read a permutation, these blocks. And what we do, it's just like what we want to do in type A, except usually we can just say, go clockwise. Here, clockwise is a little bit funny because we have an annulus. So you just keep the inside of the block on your right, and you read along. And there's a date line. This is, again, the difference between how we might read a picture like this in the annular permutations picture as opposed to what I'm doing here. There's a date line. So, for example, let's read the block in P1 that goes, that has the 3 in it. So let's see, well, here, the 3. I am moving along to here. I'm reading the wrong one. Let's see. Where is it? Oh, let's write that one. Let's see. It's got the 3, the 1. It has the 1 in it. So here I am at the 1. I'm reading, keeping it on the right, but I've passed through the date line once and then twice, and I get to the 7. So it's not 7, but it's 7 minus 7 minus 7. I have to subtract n each time, and when I come back, it comes back around. Okay, so this is how we can read a permutation, and then the theorem. First of all, the definition, you can consider non-crossing partitions with no dangling annular blocks. And the theorem then is that this map that reads permutations is an isomorphism from the non-crossing partitions of the annulus to this larger interval that in the larger group. And it restricts to an isomorphism from non-crossing partitions with no dangling annular blocks to the original interval for 1 to c. I have this sudden feeling that I've forgotten to also say that this larger interval where we put in loops is isomorphic to the McCammond and Sulway lattice that we were trying to construct. Okay, I think in the interest of time, I might skip over this. There's a way to describe simple connectors. There's a way to describe cover relations by sort of how do you connect 2 blocks and how do you cut apart 2 blocks. I'll move past that. Let's look at Krevara complementation, though. And again, just to give you the picture, the usual Krevara complementation would tell me to put a 3' there, and that's what I do. On the inner boundary, I need to actually go the other way, so I would put a 2' here, I believe, and then I look at the complement. So you see the white space would tell me that I should be connecting the 3 to the 2, and that's the block that I see down there. So anyway, it's kind of exactly what you would hope it would be if you're familiar with the Krevara complementation in the usual model. Okay, let's just quickly talk about some of the other affine types. So the usual thing that you do if you're going in finite type from type A to type B is you consider, there's an involutive symmetry, and just like we saw, right? We had centrally symmetric non-crossing partitions for type B. Well, it's the same kind of thing. The symmetry that you're seeing here, and I think also in Josue's talk there was a symmetry, and I wasn't quick enough, but I think maybe it's a different symmetry. The symmetry that we're seeing here is if we imagine that you're actually looking down a tube. So these pictures that you're seeing a perspective drawing of a big long pipe or tube, and so the smaller circle is just the farther away circle, and then you could just put an axis through the center of that tube and rotate it. That's the symmetry. So I've tried to mark, I don't know how visible they are, but I've tried to mark the fixed points of the symmetry there in each drawing. We would be taking the lattice of all symmetric non-crossing partitions of an annulus. And I just want to show that there's something nice we can do. There's dotted lines in there. The dotted lines are not part of the non-crossing partitions, but just as an aid to see what's happening. But they cut the annulus into two fundamental domains, into the two fundamental domains of this involution. And so if we want to mod out by that symmetry, we could sort of just ignore everything that's inside the circles. And then if we think about what the symmetry does, we should be gluing opposite points on the circle to each other. We just sort of, sort of collapse those circles, those white empty circles down to just a dotted line, keeping the orbifold points in the same place. And so we get pictures like this. Okay, so that's the map. Again, the nice thing about this is probably in some sense, the tidiest affine model in type C. What are we doing? We're taking set partitions of this set of integers, in this case. Okay, one has to make a choice to define a Coxeter group. And so for this, a Coxeter element. So for this particular Coxeter element, here's my 6 numbers. But you have these points, and you're taking set partitions of the points. Each block of the partition gets embedded in here, and it can contain neither orbifold point. It can contain one or the other orbifold point, or it can contain both. And if you think about it, there should be infinitely many things here, and there are, because if you don't contain either orbifold point, actually, even if you just contain one of them, there's ways to sort of wrap around infinitely and then contain an orbifold point, or not. So I just wanted to see this. So this is the model for type C. Type D it looks like Athanasiadis-Reiner, except we're on an annulus, and there's 2 double points. There's a double point up here, a double point down there. If you just looked locally where my laser is showing here, this looks like a little Athanasiadis-Reiner picture. And then there's some other things that can happen globally. You could have for example, a dangling annular block here that only contained those double points, and lots of other things. I don't have time to. Yes, we have. So there are 2 points here and 2 points there. See, what happens is when you project the orbit in this case, you get, of course, the mod n symmetry, but you also get 2 points that go here and 2 points that go here, and then that repeats mod n. So our annulus has 2 points that are double. So there's actually a plus and minus at the 6 and a plus or minus at the 1. Now, let me just take a second and say, what's going on here. I mean, in non-crossing partitions in the usual, type A sense, what was observed was that the cycle structure of the permutations that we wanted to consider was exactly, that their cycles could not cross in these ways. And if you're talking about even type A, but especially type D, these cycle structures can be much, much more complicated. So the proof that this is, I guess I haven't even showed that on the board yet, but the proof that this is modeling, the interval from 1 to C is really just a much more involved kind of thing like Philippe did in finite type A. You just have to show that as you move up in this order, you're merging blocks, and here are the possibilities, and it matches. To me, it seems a little miraculous that it would match, that there's even any way at all that you can do the interval from 1 to C in these complicated cases. But again, there's a mystery here. Maybe there's a theorem here. I don't know how. I don't even know what it would look like. But that says somehow this projecting to the Coxeter plane is telling you something. If you do that magically models like this are going to work. I don't know what the theorem is or why it's working. Okay, let me just go on. I don't know. For some reason, I felt like you needed 2 slides full of these examples, but there's lots of things that can happen. In affine type B tilde, you can, by folding D tilde, you basically get to take away one of the double points. So now this is an annulus, same symmetry, 1 double point, and maybe I'll let that be enough to say. So just to sum up, if you do the thing that's suggested by projecting to the Coxeter plane, in all classical affine types, A, B, C, D, you get a model of the interval from 1 to C. And to do that, you exclude dangling annular blocks in various, whatever that would mean in each model. In types A tilde, B tilde, and C tilde, you in fact get a model also of the larger lattice that McCammond and Sulway defined by allowing dangling annular blocks. In type D, for a very short time, my student and I thought that we had been smarter than John McCammond. This is not possible, I think. And because we thought we had a lattice in this model, but we don't. There's a little bit of information, and it's just a little bit more information you need. A finite amount of algebraic information you'd have to throw in to get the complete model there. It's still usable. The work with Eric Hanson that I will have time to almost not tell you about uses that model. You can use it, but it's just a little. It's not quite a planar model. Okay, let me just tell you basically. Not an existence proof, but I guess an existence advertisement for a definition. So a marked surface, very briefly, you have a compact surface, you choose some points on the boundary and call those marked points, finitely many of them. You use those points in cluster algebras, you use those points as the vertices of your triangulation. You triangulate your surface, you're allowed to use those points as vertices. Okay. On the boundary, and that's exactly this next point. Christian is reading my mind today. It's excellent. So in cluster algebras, you would be allowed to put points on the interior, and those would be called punctures. We're doing something without punctures here. So non-crossing partitions of a marked surface. What you're going to do, I mean, you should think, again, set partitions. You're now going to have a set partition of the marked points, and you would also like to give each block some topology. To put it in maybe very much too loose terms. I'll be around this afternoon, happy to tell people more about this. But basically, each block gets embedded as its own marked surface. It's as if each block, the embedding, it has to be a marked surface. There's some rules to say, to disallow silly things. I mean, you shouldn't make an annulus by just having a disk here with nothing in the middle, but just taking out a point. There's things like that. But basically, that's the definition. And then you take, you need to take collections of disjoint embedded blocks. Okay. The theorem is that in this case, you get a lattice, and you have a rank function that's given by a simple way. So these are Betti numbers. You're basically choosing how many different blocks you have, and you're also choosing saying something about how many circular holes, right? First Betti number, you're counting circular holes in all your blocks, and you can write this down. If you want to do symmetric non-crossing partitions with double points, in the interest of time, let me just try to say the really fast summary of this. It's just the same thing. You should just think the same thing that you saw in the type D models. You put in some points. These are like, I don't know, points in the surface, but where there's somehow magically 2 points, right? You need an involutive symmetry. Every point that you doubled has to actually be a fixed point of that symmetry. When you apply the symmetry, you also swap the double points. And maybe I will say this. The cluster algebras would tell us that we should be modding out by these symmetries and doing something with punctures, and I just don't think that's the right thing if you want to do non-crossing partitions. But let me go to the theorem. So you get a graded poset. There's a way to say the rank function. This is somehow some symmetric count of blocks and also holes. And I just want to emphasize right there, you don't get a lattice. Okay? Despite what an early posting to the archive may have said, you don't get a lattice, you get a poset and has this rank function. Okay. I think in the interest of time, I ought to wrap up here. So let me just say, let me tell you sort of what is in these slides without actually telling you what is in the slides, if you see what I mean. So McCammond and Sulway, the way that they make their bigger group is, but they take some elements of the group that are translations. They actually act as translations in the affine model. They factor them. They get new translations that weren't in the group before. They put those in. Okay, and that generates a larger group. They do the interval from 1 to C in the larger group, and that's their lattice. In type A, if you think about what the translations are, they are annular blocks with exactly 1 point on the outside and 1 point on the inside. Okay? If you read the permutations off those, you get a product of two of these things that I called loops, one sort of an increasing loop and one the decreasing loop. And if I tell you that's a translation, factor it, well, you're going to factor it into the two loops. So in type A, modulo a slight modification or maybe broadening of what McCammond and Sulway did, that's what they're doing when they factor. Okay, so the Combinatorics even understands what they mean by factoring translation. And there's similar things that happen in other classical types. And now, these are the slides. Let me think how many. Yeah, so let me just tell you, without saying, if you want, and this is something that's useful for Eric Hanson and me, if you want, you can do all this with formal symbols, right? You have a formal symbol for each reflection, and then the new thing you need is a formal symbol for each factored translation. There's actually a very nice way to say what the factored translations are in terms of the root system, that if you look at McCammond and Sulway and try to work this out, it follows from what they say, but I don't think they said it. And so you can actually just write down formal symbols and then say, what symbols are allowed to go next to each other in a word in this interval from 1 to C. Okay, so we'll skip that. And maybe I'll just leave this on the board for people to see. If you're interested in the representation theory, Eric Hanson and I are working on trying to understand the McCammond and Sulway lattice in these affine types in terms of representation theory. And if this slide is going to be interesting to you, you probably all know some of the words on it already, and so maybe I don't need to say. I can put this back up again later, but instead, let me just thank you for listening.